I'm coming back. We have Rick introducing in a few minutes one of our, the last speaker of tonight. Here is Rick, and I'll leave the floor to you, Rick.
I thought we were going to start at 6 o'clock, but I'm happy to start now. And Ken will have an extra 5 minutes. Welcome everybody who's new to the program this evening. We've been talking all day about things relating to interdependency and how cities relate to each other, and particularly with the sub-theme of the day of tools. What are the areas of expertise, specialization, and manipulation that get to the heart of the theme of this year's Biennale. Tonight at 6 o'clock, we are very, very honored in talking about not only interdependency, but interdisciplinary work, to have with us Kenneth Huber. Ken is an engineer working at Langen, a firm that is remarkable for the work that it has done, not only in New York, but around the nation. Cross paths with your colleagues, Ken, after Sandy, with the work that the firm was doing at Baruch houses to bring back some of the habitability issues, systems issues, livability issues in public housing projects that were so close to the waterfront, impacted on the Lower East Side by Sandy. But my job here is not to laud Langen, although I could do that easily and at some length, but to talk about you. And the bio in the Biennial website is short and sweet. It says that you're a senior project manager with Langen. You obtained a Bachelor of Engineering in Civil Engineering from Stevens Institute of Technology, a great school, back in 1993. I'm presently teaching in the Civil Engineering department at Columbia. We compare notes all the time, not you and I, but Stevens and Columbia. And that you have a Master of Science in Geotechnical Engineering from Virginia Tech, conferred in 1997. It says, therefore, you have over 20 years of experience in both geotechnical and waterfront engineering, and you hold professional engineering licenses in 3 states. Doesn't say which ones, but I'm guessing New York is one of them, probably New Jersey as well. And that you lead Langen's waterfront engineering practice here in New York City. You know, that says probably all that we need to know, but I'm going to embellish it a little bit because I'm impressed. You and I don't know each other. At least I don't remember being on the same projects. Maybe when Wedge was introduced at the Center for Architecture. I know that you're a strong proponent, an early adopter. One thing, you know, about Langen that I might add, you know, from the website, your section on it, it says that with many offices on or near major bodies of water, Langen serves all major coastal regions. This means that you don't have to do this, you know, if you don't want to take time on it, as well as river and lakefront properties. So from the boathouse pier in New Haven to a bulkhead beneath a residential complex in Tampa, you might want to talk about, you know, Ian a little bit, time permits, and from a levee for a massive new pump station near New Orleans to a WAF evaluation at oil terminals in the San Francisco Bay Area, Langen knows how to help land meet water. There's an interdependency. But frankly, I was more interested in an interview you did with, I guess, someone from the Metropolitan Waterfront Alliance a while back after Wedge was launched. And you were not only an early adapter, but a strong proponent, because it talked about your background in a much more personal way. And I'm just going to read something that was an answer to a question of why you do what you do. And it says, quote unquote, I grew up about a block from the Salt Brook, a little stream in northern New Jersey. I live not all that far from there, so I know it well. It doesn't say that. That's an editorial aside. We used to play in the stream regularly. I started my career working on projects in Jersey City on the waterfront and quickly grew to love it. The projects are interesting, the design is challenging, and the results are rewarding. I started my first waterfront projects more than 25 years ago, and I've loved working on the waterfront ever since. I think we'll hear about more than just the waterfront, the interdependency between different places. Water is a connector, it's a separator, but it's a connector historically and currently. I'm really fascinated by what you do, Ken, and I'm looking forward to hearing a lot more about it tonight. So the floor is yours.
Thank you, Rick, for that kind introduction. I have been doing this for over 20 years. I absolutely love it. And the challenge of the waterfront is the interdisciplinary nature of design. And so this will be a little bit different than what you may have heard in the rest of this conference. We're going to focus a little bit on engineering. And I wish I could share even more with you of how the engineering at waterfront properties intersects with architects. But with limited time, I'll give you a little bit of a primer, show you some ideas that might be important for you to understand and incorporate into your practice. And as always, we're available to assist if you find yourself in a waterfront development project that requires some expertise. So with that, let's dive in to the presentation. Give me a moment and I'll share my screen and we can get moving. So we are focused on sustainable waterfront development and all that goes with that. I've been doing this for a long time, and these are some key principles. We're going to talk about two questions today: why waterfront and what's so difficult about waterfront. So let's begin with the why. First of all, it's important to understand that civilization was born at the waterfront, and all of those massive ancient civilizations that we know about and study, they started at the water's edge because of the dependency they had on the water to begin that civilization and support that civilization. And quite frankly, not much has changed, at least in the US. Our major cities are either on coastal bodies of water or inland bodies of water, whether that be lakes or streams or rivers, because we still have that kind of dependency on the water for sustainability and success of that urban environment. And so I'm primarily focusing on urban waterfront redevelopment, but these same principles can apply beyond that. So let's track the history and understand how waterfront development has occurred in history at the water's edge. So these images that I'm sharing on this particular slide all come from Red Hook in Brooklyn, New York. And they track the history of development at that area of New York. So initially, as settlers arrived to this country, you would see small fishing and farming villages pop up along the shoreline. And then as more and more people came, the waterfront became a hub of transportation and commerce. And it was the highway of long distance transportation and commerce. As more and more products began to be shipped via the water, Red Hook in particular became the most highly developed and frequently used port in America in the 1960s. So this became a huge part of the New York City economy in mid of the last century. But as shipping has moved away from the water, pun intended, into other forms of transportation, those properties have become dilapidated, decayed, contaminated from years of industrial use, cut off from the surrounding neighborhood, and really falling into the water, causing even more contamination. And they've become an eyesore. Something needs to be done. And what we found consistently, time and time again, with few examples shown on the screen, is that when we redevelop, revitalize a particular block at the water's edge, what happens is the neighborhoods around it begin to be revitalized as well. And so investing in a small section of the waterfront can have a radical impact on the surrounding neighborhoods. And I want to share with you a case history from Jersey City, specifically Paulus Hook. So we start in 1767. On the left-hand side is the shore of Jersey City, and Paulus Hook is in the red box at the bottom left of the screen. On the right side of the map is Lower Manhattan, and you can see in Lower Manhattan, there are piers that are starting to jut out into the water. and it's fairly densely populated. But in Jersey City, that's not the case. That's the natural shoreline. It's unaffected yet. And you can see small dots on the map that represents a small village. That's all that's there in 1767. Well, by the turn of the century, you can see everything on both sides of the Hudson River have been fully built up. There are piers at just about the end of every street. And on the Jersey City side, the left-hand side, you can see a tremendous number of rail lines that terminate at piers where goods would be shipped over the water to the piers, transferred onto rail, and taken across the country, and vice versa. They'd come in by rail, transferred to ships, and around the world. And our particular site, again in the red box, that was occupied at this time by the Colgate-Palmolive Company. They occupied 14 blocks in downtown Jersey City, and this was the center of their operations. And from this point, their goods were sent around the entire world. You can also notice that they have 4 piers within their property, and you'll notice how that changes over time. In 1978, they're about a decade before closing their facility. You can see that things have already started to change. Several of the piers are dilapidated or falling into the river or even completely gone. And really only one of those piers is functional. We'll take another view of that. You can see on the left-hand side, in full operation, peak of operation, 1966. Even then, a couple of their piers have already become deteriorated, falling into the river. And that's at the peak of its shipping. And in 1988, on the right-hand side, only 1 pier remains. And you can see highlighted in yellow that Colgate clock, just to give you perspective on how these two images relate to each other. What you couldn't see in that aerial is the condition of the shoreline. That's shown here. On the northernmost section, the bulkhead had collapsed, and all that was left was a rubble shoreline. In the middle of the site, the sheet pile was so deteriorated, it had corrosion holes all the way through the sheet piles. And you can see that in the middle photograph. And then on the southern side, you can see where the sheet piles are bowed out. And that's actually a collapse. Those tie rods snapped, and that section of the bulkhead started to fall into the river. So obviously something had to be done. And this site's contaminated from years of industrial use, so that cleanup needed to take place. And this bulkhead is not providing a reasonable cutoff to prevent cross-contamination of those contaminants. The site's also cut off from the surrounding neighborhood, literally by fences. The streets themselves are inaccessible to the public. And the infrastructure is so old and falling apart that it could not support future development. So Colgate decided to invest in some infrastructure improvements to allow for future development to take place. I'm going to go through some of the key aspects of the improvements that they did. And first off, they replaced the existing bulkhead with a brand new bulkhead to protect the shoreline, prevent it from further eroding, and also allow excavation of contaminated hotspots upland of the bulkhead. You can see some of that excavation taking place there. That bulkhead also serves as an effective cutoff to prevent migration of contaminants into the body of water once it's finished. Immediately behind the bulkhead, they installed a brand new 8x10 box culvert combined sewer outfall. And this box culvert connected 3 combined sewer outfalls and redirected them to a screening chamber at the far south end of the site. Jersey City was working on the screening chamber, and Colgate worked with Jersey City to design this box culvert to connect to it. So 3 combined sewer outfalls that dumped raw sewage during storm events were now taken out, redirected, and are run through a screening chamber before they discharge. And that takes out a lot of the large particles and floatables that are in the water before anything gets discharged. And that's a significant improvement over what was there before. Now, mind you, we would love to see more done to improve combined sewer outfalls, but this was a huge step cleaning up 3 combined sewer outfalls in one project. Colgate also worked with New York Waterways to install a brand new ferry landing at the facility, and none existed before. It wasn't planned before, but when Colgate began to talk about the possibilities of future development, New York Waterways saw the potential and joined in the project, and we helped develop a ferry landing to go with this redevelopment project. That ferry landing is 2 blocks south of the Exchange Place Path Station, and so there's a subway nearby. You can see a parking lot right behind the ferry landing, so there's parking where you can park and ride. And furthermore, just 1 block to the west of the shoreline is the New Jersey Transit light rail system. Again, no station was planned, but Colgate worked with New Jersey Transit to install a new station right at the site, and also worked with them to allow for infrastructure improvements, new utilities to be placed below the new light rail lines to support future development. So you've got an intermodal transportation hub within 2 blocks right here: park and ride, light rail, ferry system, and the PATH subway. And they finished it off with a beautiful esplanade that's open to the public. And on a nice day like today, you can go out there on lunch and really enjoy the views of Lower Manhattan. It's absolutely beautiful. And what amazes me is this was 4 blocks of shoreline, roughly 1,200 feet. But what's happened since is a complete revitalization of downtown Jersey City. Shorelines both to the south and the north have been improved for many blocks. And we've seen brand new development take place, not just on those 4 blocks adjacent to the waterfront, and not just all 14 blocks of Colgate-Palmolive, but throughout this neighborhood. It's had a huge impact on redefining Jersey City. And this is the sort of thing that makes waterfront improvements and sustainable waterfront development so exciting, because it can have such a radical impact on the neighborhoods along the waterfront. So let's talk a little bit about what's so difficult about waterfront development. And we see a picture on the right, or sorry, on the left, of what we think about when we think about going to the water. We think about a nice beach, calm waters, being able to get in, recreate, swim, get in our boat, enjoy ourselves. But we often forget the absolute destructive power that water can bring. And as designers, we need to respect that power, as we've seen in Ian and up in New York City, as we saw in Superstorm Sandy back in 2012. Water has incredible destructive power, and as designers, we need to respect that and build that into our design plans. So let's take a look about what's so difficult of waterfront construction, waterfront design, waterfront development. The first thing to consider is what we just talked about: flooding and storm surge. And what you see in front of you are flood maps. Both of these maps are published by FEMA, the Federal Emergency Management Agency. And these are flood insurance rate maps. They show the level of inundation for a 100-year storm, 500-year storm as well. But these maps are predictive models. They offer a snapshot in time. So the one on the left was published in 2007, and it's a predictive model of where 100-year floods and 500-year floods may inundate during that type of flood. The one on the right was generated in 2013, and you can see that there's more blue on that map than there was in the 2007 map. And this is not because evaluation procedures have improved, but because floods actually are getting worse. And we see that the 2013 map, which was published just a year after Sandy, but did not consider Sandy in its model, it actually matched Superstorm Sandy. The inundation map for Sandy is shown now on the left. You can see that the predictive model is actually very close. The problem, of course, with the 2013 map is that it didn't consider Sandy. And so future storms may be even larger, and that now is being considered by FEMA. And these 2013 maps will be replaced in the next 3 to 4 years. So you can be looking forward to that. In the meantime, we here in New York City, and often in surrounding states, need to consult both the 2007 and the 2013 maps and see which is worse and design for that until better maps become available. This sets what's called our base flood elevation. So what level of inundation can we expect? And let's say from this map, it's roughly elevation 10. So that's our base flood. That's where water levels will rise during a storm. But again, that's just a snapshot. And just as was talked about in the previous presentation, we need to consider things like climate change and sea level rise that results. Now, I want to be clear, sea level rise is not a new phenomenon. It's a known fact. It's been happening for hundreds of years and has been documented. The part that we are not so familiar with, what we are trying to predict, is the impact climate change can have on sea level rise. And these curves that you see on the screen in front of you are predictive models. And each of these curves consider risk and probability to estimate where could the level of inundation be. How much could that sea level rise in a given period of time? So the blue line simply maps out the historic trend. We continue to see inundation occur as it has in the past. The other lines are predictive, and each of them has a particular risk associated with it. So at the highest level, that magenta line at the top, maybe that has a 5% chance of exceedance. Whereas the blue line all the way at the bottom, that may have a 95% chance of exceedance. So there's risk associated with each of these lines. And let's say we want to assume a moderate level of risk, say 40 to 60% chance of exceedance. And we're looking at a building 50 years out from today. So that's that vertical yellow line that rises on the graph. So we would be looking at a prediction of somewhere between 1 foot and 2.5 feet of sea level rise. Those are those two yellow dashed lines on the chart. So we have our base flood elevation from FEMA, but that's a snapshot in time, and our building needs to last for 50 years. So we need to see how much sea level rise we need to understand and design for. And then we need to put that all together. So we start with our base flood elevation from the map. We add to it our sea level rise from the predictive models we just looked at. Then we add to that the code requirements for a particular freeboard. And those codes are changing, so you need to understand your local building code and apply the required freeboards. And that gives us what's called our design flood elevation. Now, everything else that we talk about from this point forward is related to that design flood elevation. Now, we can set that design flood elevation where we feel is appropriate based on that sea level rise. We can even provide a larger freeboard than code requires. And zoning code allows us to do that in most jurisdictions. But we, as the design engineers, we as the design professionals, need to come to the table and make an assessment of where we think we want to design this particular project for. That's up to the design professional. So once we've set our design flood elevation, we have other things to consider. And this is where things continue to become difficult at the water's edge. The next thing to consider is loading. So when water inundates a particular site, hydrostatic loads occur. Hydrostatic meaning it's water that's not moving, simply by being there. Loads are imposed on the side of the building because the water wants to push in. But loads are also applied underneath the slabs of the building. So for example, if your building has a basement and that site gets flooded, that basement is well below grade. And the deeper you go in water, the more pressures push up on that slab. And we need to consider that because a slab, a basement slab, can fail under hydrostatic pressures. Even if nothing moves, even if the water stays still, that pressure can pop a slab and cause extensive damage inside. We also need to consider that in flood, those waters are moving, and the movement of that water increases loads on a structure. It pushes against that structure, causes drag along the sides, and we even have crashing waves if the storm water is high enough. Furthermore, we need to think about impact because there's floating debris in this water, this flood water, and we need to think about wave runup. So waves are crashing on the shoreline. The flood may not reach us, but maybe the wave runup does. We need to think about those things, particularly when we're siting our building. Where are we going to put it? Can we put it back far enough that it's not going to be affected by a storm? We also need to consider things like scour and erosion. So on the left-hand side, you can see an image of a collapsed slope. Those trees are not growing that way. The slope has failed and slid down. And so those trees are at weird angles because the ground they were in is now at the bottom of the slope. And you can see the building behind that slope is very close. This slope failed during Superstorm Sandy, and technically it failed as those floodwaters receded. As those floodwaters went away, the saturated water in the slope came out of the face of the slope and pulled the water, the slope with it, took the soil right down with it. And this is not uncommon. This has since been repaired, but you can imagine if that slope failure was deeper, that building could have been damaged. And on the right side, you see the effects of scour, where you've got a hard bridge pier and water trying to rush around that hard obstruction actually digs out the soil around it and can undermine the foundation. So these things need to be considered and their impact or potential impact on the buildings that we design and the sites that we design. So I want to talk a little bit about the kind of waterfront elements that are useful in protecting our properties. So we'll start with our shoreline protection systems, and I'm going to list these types from least intrusive, most environmentally beneficial, to most intrusive, least environmentally beneficial, but they will also be on an increasing scale of robustness. So we'll go from relatively weak to incredibly strong shoreline protection systems. So first is a vegetated slope. And everyone likes to do this sort of thing because they're incredibly helpful to the environment. We're building new wetlands, and wetlands are an incredibly valuable resource for habitat. There are thousands of species of organisms that live in these systems and grow in these systems. There are thousands more of birds and animals that stop by for various periods of their life to feed or to reproduce. These are incredibly important. However, they're not very strong. And so these are reserved for areas of low flow, low energy, like protected coves. Next is a revetment. And a revetment consists of a slope and some form of armoring. In this case, in the picture from Shore Parkway, this is riprap or stone type armoring, but the armoring can also be concrete blocks, concrete jacks, mattresses, gabions, all sorts of things. And sometimes these kinds of revetments are also planted, so they can have greenery that grows through the armoring. In this case, it's just riprap, but the riprap or the armoring creates these nooks and crannies that organisms can live in or hide in, and the armoring itself allows encrusting type of organisms to grow and thrive. So this is pretty good from an ecological standpoint, and it's significantly more robust than a vegetated slope. The next is a relieving platform. A relieving platform, this one is a high-level relieving platform. Most are low-level, but low-level platforms, you wouldn't see the structure because it's below water. This one, you can see it. There are piles supporting a platform with soil on top of that platform and a head wall at the front of that platform to hold back the soil. But water can get underneath that. So that means there's still some habitat that's protected. Now it's mostly for predators because it's shaded, so you can't get encrusting organisms. And those that are lower on the food chain generally don't want to go in those dark spaces. So this is limited in its habitat creation, but it does provide some. And it's very robust in its protective level. Next up is an anchored sheet pile bulkhead. You can see a steel one in the background here, but they can also be made of plastic, wood, fiber reinforced polymers, etc. Most common is steel, like as shown in the photograph. They're very thin profile, so the thickness of that steel is only about 1/2 inch or less. They are fluted so that they gain strength by their corrugations. So they have very little impact in the environment because they have such a small footprint, but nothing grows on them. So you've got no environment that's created, no habitat. And the next is a gravity seawall. As you see in the picture here, this one's from Roosevelt Island. You can see the amount of disturbance required to construct one of these. They are very disturbing of the environment, but they're also very robust and good for where you have high loads. And then lastly, the most disturbing is a cellular cofferdam. In each of those circular structures where the cranes are located, those are cellular cofferdams. Think of them like a barrel filled with sand. They're just large barrels. So the hoop stresses of the barrel holds everything together so it acts as one unit, and the sheer weight of that unit is what resists the loads. These are generally reserved for very deep water and very high loads. In this case, it's for the Rion-Interion Bridge in Greece, and it was only temporary. It was there for the period of construction and then removed. But you can see how large those structures are and how much of the water needs to be filled in order to construct them. So now let's talk a little bit about waterfront structures that may support our shorelines. First is a floating dock. These are often used as kayak launches or swim platforms. They allow people to get at the water and into the water for recreation. A little bit bigger floating dock is a ferry landing. Similar idea. It allows people to get to the water and specifically to load onto ferries or other vessels for transportation. Then we have a breakwater or wave screen. These reduce the energy that the shoreline protection system needs to provide by breaking those waves before they reach the shore. This particular one at New York Police Department Harbor Unit. Next is a flood wall, and you may not think of a flood wall as a waterfront structure, but quite frankly, in a flood, that's your waterfront. So those are waterfront structures. Next is a breasting dolphin. Breasting dolphins are used for shipping exclusively. They're a little bit less intrusive than piers or wharves, which we'll look at in a second. They allow ships to come up alongside groups of piles, and those groups of piles are connected by small catwalks. So they don't occupy as much space as a pier or wharf, but they also do allow for the transportation of goods from a ship to the land. Generally, we're looking at liquid or powder type products for distribution in this type of system. And then we have our wharf. Our wharfs are parallel to the shoreline, where water is generally already deep at the shoreline, and we need a flat surface in which to load and unload. And then piers are perpendicular to the shoreline to get us out to deep water where the shoreline is shallow. This particular one is Pier 17 and has a building on top of it, but historically, piers are used for shipping. And then just a brief review of our water-dependent uses. These are uses that have to be at the shoreline. They can't be elsewhere. They can't be relocated. So first is a beach or get down. This particular one at Damava Park, which is just south of the Colgate-Palmolive redevelopment we looked at earlier. Then we've got a waterfront park Many of our piers and wharves are being turned into parks at this point. We have a promenade or esplanade, this one at J. Owen Grundy Park, which is in Jersey City, just north of the Colgate-Palmolive development we looked at before. And then we have boathouses, marinas, this particular one at Battery Park City, where we store our vessels, and then ports and terminals, which are exclusively for shipping and industrial purposes. So those are the tools in our toolbox, but that's not the only consideration that we need to think about. In fact, our last speaker spoke about materiality, and that's what we need to consider now. Durability of the materials that we use at the shoreline. So we may think, well, let's use timber. That's a natural material. It's green in that it can be grown and regrown as we need it. And that's certainly true, but timber has a poor record of durability at the water's edge. Now, timber used to last a long time. It was used in the 40s and 50s and 60s almost exclusively. But then our harbors were far dirtier than they are now. And as our harbors get cleaner and cleaner, we see that the deterioration of timber increases, becomes more rapid. There's a reason for that, because the organisms that cause that type of deterioration are coming back. We'll talk about that in just a moment. But what you can see here is that there's been so much deterioration in this particular wharf that the tops of these piles are now completely gone. And the middle of this pile is gone so that the top is no longer connected to the bottom. And over here, there's a giant hole in the center of the pile. The pile is hollowed out. So what causes these kinds of deterioration? Well, first up, we have the teredo or shipworm, and it creates burrows in the wood. And that burrow becomes its home, and it will stick its tentacles out from that hole to eat. It's a filter feeder, but it causes these holes. And on the outside, it may look like this, but on the inside, it creates Swiss cheese, all these burrows throughout the wood. And this is what can hollow out the inside of a piece of wood. The second organism we need to understand is a limnora. And a limnora doesn't create burrows. It actually eats wood, and it eats it from the outside in. And that when we get this hourglassing type of look, that's caused by limnora. And these two organisms are on the rise in New York Harbor because we're doing a good job cleaning up our harbors at this point. So timber becomes less and less desirable in the harbor as the harbor gets cleaned up. Now, there are things that we can do to protect it, like inject chemicals into the timber, but that comes with its own problems. So let's look at other materials. Perhaps maybe we'll look at steel. You may think steel would do a great job, but steel, as you probably know, is subject to corrosion, and the saltwater environment in our coastal shorelines is extremely aggressive in corroding steel. And even our inland bodies of water, the constant wetting and drying is also extremely aggressive. Not quite as aggressive, but still extremely aggressive in causing corrosion. And you can see here that in these sheet piles, there's so much corrosion, the corrosion is eaten all the way through the sheet piles at the waterline. And in fact, there's so much corrosion in the whale that it's bent. It's no longer working the way that it was intended. You can even see the corrosion in the bolts connecting timber elements. And in some cases, those bolts are so corroded, they're completely missing. So steel may not be the best material in the water either. Now, again, there are things that we can do to protect that steel, like put in coatings or provide cathodic protection. But in order to do that, we need to understand how steel reacts in water. So in a tidal body, coastal waterfronts, we have several zones that we need to be aware of. We've got first the splash zone above mean high water. We've got the intertidal zone between the tides, mean high and mean low. And then we have low water just below mean low water. Then we have the part that's always immersed and the part that's buried in the ground. Now let's take a look at corrosion rates. Corrosion rates are highest in the splash zone and low water zones. Hence, the corrosion that we saw at the low water zone in one of the previous pictures. We get moderate rates of corrosion in the intertidal zone, and then things drop off in the immersion zone and the buried zone. We need to compare that with where our maximum moments are, where this sheet wants to bend. And those occur at the tie rod and generally somewhere in the immersion zone, not at where our highest rate of corrosion is. So we can accommodate that. We can think through that, where we're going to get corrosion and what kind of maximum moments we're going to get there. But we do need to think this through, or we need to protect for it. So you might think, well, maybe steel's not the best material. Let's consider concrete. But concrete doesn't perform much better. It has its own problems. As salt water begins to penetrate into the concrete, the reinforcing can corrode and pop off that concrete, and it can do extensive damage. So we need to be careful even in specifying concrete, in understanding the kinds of concrete that are appropriate to use in the marine environment, how to use steel, reinforcing steel in the marine environment, and also provide sufficient cover to protect it. So you may think, well, none of these materials work. And that's true. That's the difficulty of waterfront improvements and doing waterfront sustainably. We need to select materials and protect those materials, but we also need to think about maintenance. In the waterfront environment, coastal waterfront in particular, inspecting and doing regular maintenance on those structures is absolutely crucial to their long-term success, and not having to replace those structures shorter than we should. So keep that in mind. Materiality of what we do at the water's edge is extremely important, but so is regular maintenance, and that needs to be communicated to our clients. As the design professionals, that falls on us to communicate that. I want to end talking about one of the last obstacles on waterfront construction, and that's permitting. And permitting can be an absolute nightmare. It can be very challenging to work through all of the agencies that are required to provide approvals before waterfront development can move forward. So the first level, and this goes pretty much anywhere in the world, there's a federal level that's generally required for approvals. Now, here in the US, that's generally the Army Corps of Engineers. They're going to usher that through the federal agencies and get that reviewed at the federal level. So we submit to the US Army Corps of Engineers, they review it, and they coordinate with other federal agencies to get a permit issued. Except if you're in a Superfund site. So if you're in one of the nastiest water bodies in the world, like the Gowanus Canal, the Environmental Protection Agency of the US is the agency that governs that. They will oversee that, and they will waive all other permits. They are the final arbiter of what will be approved. So unless you're in a Superfund site that's being cleaned up, you're going to have to go through all three levels of permitting. The second level is the state level, and I generally practice in New York State. So what's listed here is the New York State agencies. So the lead agency is the Department of Environmental Conservation. They're the ones that are going to issue the overall permit, but we also need to talk with Department of State for a coastal consistency review, and we need to talk to the Office of General Services to determine if there are lands owned by the state underwater that also need permissions. Now, these two are generally submitted at roughly the 30 to 50% design stage. So maybe schematics or 50% DDs. That's when shoreline design gets submitted for permits to both federal and state levels. They occur concurrently, and the permitting process can coincide with the design process. But then at the local level, this occurs, normally it would be your local building department. And this occurs at the end of design. In New York City, the reviewing agency is Department of Small Business Services. And in addition to that, Department of City Planning also reviews development at the water's edge. Now, in other agency or in other jurisdictions, that can be the local building department. But it's important to know these zones where waterfront permitting is necessary, and they may not agree with each other. So coordinating between this is a significant effort. And it's important to understand the impact on the schedule. And then it's also important to know when a permit is needed. So moving from right to left, there's a portion of the site that's always underwater that requires a permit. Then there's the tidal wetland, which goes all the way up to mean high water line for the state level in most states, and up to the spring high water line at the federal level, at least here in the US. It can extend if there's vegetated wetlands, it can extend up to the back of any vegetated wetlands. That's the tidal wetlands area. And then beyond that, there's usually a buffer, and that buffer is assigned generally by the state. And that buffer size varies by state and locality. And now in New York City, it's 150 feet and it's called an adjacent area. Anything in those three zones, the always wet, the tidal wetlands, or the adjacent area, those are going to require permits. So it's important to understand that and to budget your schedule accordingly. I wish I could go into so many other things, but we are out of time. And so I'm going to conclude my presentation here and just remind you, the reason that we do waterfront is because it has such an incredible impact on our neighborhoods and environment. And we need to respect its power and design accordingly.
Ken, I want to thank you. That was a great talk because, among other things, it gave those who aren't in the engineering profession an insight into the toolkit, the tools, as you described them, that allow for everything from greater habitat to resistance, resilience, even permanence in some instances. It was fascinating to see some of the images from Jersey City, and how that transformation has had both community development and economic development benefits. Issues that certainly do relate to our theme of connectivity. And you touched on other places that you've worked with Langen at Gowanus Canal, the projects there. There are many others that you might have mentioned that would have been just as fascinating. There was one image of Roosevelt Island. I know you guys were working on the FDR Four Freedoms Park. But I have a question that relates to those, I'll call them architectural or urban design images rather than the engineering details, which has to do with, call it accessibility. I think the big transformation in the New York waterfront, I was working at city planning in '76 as an intern on coastal zone management. I've worked on tugboats, lived on houseboats in New York Harbor, and the transformation is phenomenal, all in the direction of greater public accessibility, greater amenity, from the promenades and esplanades that you've worked on and described, to cultural facilities, more housing certainly, and certainly more parks. Balancing that greater public access with enhanced risk attendant to storm surge, sea level rise, extreme weather, climate, chaos. Do you consider that the engineers, can't think of the right word, challenge,
Yeah.
burgeon the toolkit, or is there a tension that makes you sometimes lose sleep at night or throw up your hands? That's my one and only question. Then it goes back to Natalia after your response.
Yeah, it's incredible. I actually had to remove some of that discussion, Rick, from the presentation just for length. But there are tools to consider, and think of what they've done at Governor's Island with the Hills Project in trying to accommodate sea level rise and increased risk for flooding, to still have park and park features that are accessible and allow people to use them years from now when we are facing that sea level rise. Things like that are important. Designing your get down so that they work not just today, but 50 years from now during the life of the project. So yes, those are incredibly challenging from a design perspective, because as you can imagine, the architect has one idea, the landscape architect has a different idea, the civil engineer has a third idea, and the waterfront engineer is like, well, I can't make those work structurally. So all of those folks need to come together and figure out, okay, what's permittable, what's best for allowing access, not just today, but in the future. Yeah, it's incredibly challenging, and it requires a multidisciplinary approach.
Well, my hat's off to you and your colleagues for the work that you've done and shown us tonight. And I think maybe Natalia has other questions, or members of the audience do, that she will channel with some help from her colleagues in the Biennial. But I want to thank you for a great talk. Really appreciate it.
I can, well, first of all, good to mention, we worked together in one of the projects here in Brooklyn. And through that project, I learned a lot about the technical aspects involved on retaining the water. And, I thought that it was great to bring to the audience the knowledge that I acquired through you to, so many others that need help when designing, especially, cities that are on the waterfront. We have audience from all over the world, and as you said, is something that is a tendency, but we need to be very aware of the danger of being close to the water. I cannot imagine how many people need your expertise right now around the world. Then one of the things that I learned that it was not mentioned is like here in New York, and as a regular citizen, you would see all these piers that are almost destroyed there, and they're there, and you're like, why they don't do something with them? One of the things I learned is that it's not easy to start something from scratch. So people want to keep the historic aspect of it to build over. Could you tell us more about it? Why it's so valuable to have them, all destroyed there?
Yeah, so piers are incredibly difficult to permit. And if you've already got one, you really want to preserve it and be able to use it. So that maintenance that we talked about before is absolutely crucial in order to allow these structures to continue to be used in the future. And unlike buildings, they deteriorate much more rapidly as a structure. So you think about bridges, and that bridges are required to have regular inspections every year or two, right? We don't do that with our buildings. We just don't. But when it comes to our waterfront structures, we have to pay attention to that. And from a resiliency perspective or a sustainability perspective, it requires so much less to maintain our structures, to repair our structures that are already in place, if possible, than to replace them entirely. So from a sustainability perspective, it's absolutely essential that we do our best to try and reuse the structures that we have. And from a permitting perspective, it's much easier to maintain than it is to replace.
Yeah, no, that was something that it kind of opened my eyes of why New York has so many piers that are all destroyed there. And no one, if you don't have the money or the availability to go through all these permits that are so hard to obtain, they are still there, and no one moved them. No?
Yeah.
But anyway, I think one other thing that I need to do before you go is to say thank you to Langen and you for your time, and also say thank you to the audience that is staying with us for so long. We have public from Ecuador, the Universidad Central de Ecuador. The students were waiting for this little salutation for a while. So I'm sorry it couldn't happen before, but I hope that they all learned something from you. And thank you for staying with us tonight. I know they are meeting and listening to the conference as a group.